Welcome everyone to another video, the first one in a long time that is once again related to satellite reception. Today I want to talk about Starlink, and I believe this is the first time I'm actually talking about Starlink on this channel, at least in a public video. There are some unlisted videos where I attempted to receive something from Starlink, but those are long outdated. So Starlink satellites, there are quite a few of them, one might say even quite many of them. And if you have done any sort of SDR reception, satellite reception, or just radio reception in general, you might have started to wonder if there are this many Starlink satellites, surely there is something that can be received from them using an SDR. And that's exactly what I want to show you in this video. Now, this is nothing new. In fact, back when this story begins together with Starlink. So when Starlink was first rolling out in Europe for the first time ever, there have been attempts by amateur radio operators or just satellite reception enthusiasts, such as myself, to receive something from these satellites. And my hope was that these Starlink satellites would transmit some narrowband signals in any capacity. Now, why specifically I was looking for narrowband signals was because if you take something like an RTL-SDR v3, those only can receive, and I say only in quotation marks, a couple megahertz, maybe 10 megahertz, maybe 20 megahertz with the RF. But when it comes to internet traffic, which is what Starlink is for, we are talking about dozens, up to hundreds of megahertz of channel bandwidth at a time. That means that even if you have a setup that can receive these radio signals, you're not really going to be able to see much on the spectrum with an SDR. Sometimes you can see like some patterns in the signal. That's what I was wondering about. And I didn't really get any answers. Well, I did get an answer there. SpaceX did fill out an FCC, report, a request for the band allocations, and they did actually talk about the channel bandwidth being like 250 megahertz. In fact, okay, we're gonna be taking a look at that later. I'm not reading off script anymore, so I'm just trying to concentrate to get the story straight, so it makes sense. Before these satellites were first launched, we already knew the frequencies they would be using and the bandwidths, the channel bandwidths that they would be using, and notably, there was no mentions of any sort of narrowband downlinks or narrowband emissions. Normally with satellites that use very wide bandwidths, for example, Landsat or other Earth observational satellites, even if you cannot build a setup that can get anywhere close to being able to receive that bandwidth, they usually use some lower frequency band. So for example, Landsat again, it would downlink like dozens or hundreds of megahertz wide signals in the X band, but alongside that would use some comparably narrow band signal in the S band. So that's a lower frequency band with a much narrower bandwidth that you can actually track with an SDR. And I have done that when Landsat 8, I believe, was launched. I was actually able to see the entire signal bandwidth in the S band, the tracking telemetry signal, whatever. So that's what I was kind of hoping for with Starlink, that we would get some tracking beacons at least, similar to geostationary TV satellites, and that, I don't know, they plan to have like 30,000 satellites. Maybe you could do at least something marginally fun when you can sort of try to build up a personal collection of contacts with Starlink satellites, contacts again in quotation marks, where you would just be receiving some tracking beacons and, putting them on the list, what you receive, whatever. I don't know. It's really, it sounds stupid, but that's what I like. So that was what my hope was, right? And then the Starlink service was rolled out in Europe, and people started looking. I don't know if it was the first person to receive anything from Starlink satellites using an SDR, but it was the first person who I have seen receive anything from the Starlink satellites with an SDR, was Oleg Kutkov, whose blog I will link in the description, whose accounts, social media accounts, I will also link. I highly recommend you check him out, not only for his electronics related projects, but also his efforts to help Ukraine. This was documented on Twitter, but of course the new management has completely broken the search function, so I can no longer find those tweets, and I can't even scroll that far back in my own account, so that's just gone forever. I'm now looking at my own blog post. Oh, I actually have the tweet linked in my own blog post. That's really useful, so I'm gonna link that in the description as well. So it was a post from Oleg Kutkov on November 14, 2021, where Oleg basically is showing a screenshot in what looks like GQRX of a bunch of carrier waves, what look like unmodulated carrier waves. I'm gonna call them carrier waves. It's probably not the correct term to use here. It definitely isn't from what we're about to learn later in this video, and I'll put it on screen. There's even me asking in the replies what frequencies are in these broadcasts on, and he replies 11.325 gigahertz. So this was, as far as I'm aware, the first, or at least one of the very first receptions of these signals. And yeah, immediately looking at that, first thought, these have to be Doppler tracking beacons that maybe SpaceX is using to aid them in generating TLEs or predicting the orbital paths of the satellites, because obviously a stable, unmodulated carrier wave is very useful for that. And that's sort of what I based my subsequent blog post about, and there's the chances that you have read that are not really that small, because the same blog post has been shared by the RTL-SDR blog. And if we go through it, you can see that I am basically demonstrating how these signals can be received. Now, they are quite strong. They are much stronger than what you would expect. So the Starlink satellites actually use the same downlink band as SKU band TV satellites do, between 12.7 and between 10.7 and 12.7 gigahertz. Now, I'm not sure if that's exactly the range. I think it is, and I think TV satellites also go a bit below and a bit above that. But the point is that it overlaps with the TV frequencies, which in turn means that you can use a satellite TV LNB, off-the-shelf available satellite TV converters that you can get basically for free when people are trying to get rid of them, or you can buy them brand new. Again, I've shown some on my channel, and all you have to do, you don't even need a dish, right? Normally we'll take the LNB, mount it in the focal point of a dish antenna. The LNB then collects the signals focused by the dish antenna. These Starlink beacons are these Starlink signals are so strong that you don't need the dish antenna. You just take the LNB, connect it to your SDR, power it up somehow. We're gonna talk about that again. Aim it at the sky, and then you just wait. If you look at the screenshots in the blog post that I made on 25 November 2021, so that was 10 days after Oleg's tweet, there are some screenshots of the frequency 11325 MHz in SDR sharp, and you can see it is full of activity. And if you go to some of the videos and some of the blog posts of other people who have basically repeated the same experiment, they also see the same thing, where you just have basically at any given point in time, by just aiming the LNB straight up into the sky, it will be receiving these carrier waves from some Starlink satellite, even back then when there was nowhere near as many satellites as there is today. So that was the reception at 11325 MHz. And as people have been doing this after I released that blog post, either people inspired by it or people who have read about it on the RTL-SDR blog share, or people who have just done it independently, it came to light that there are more frequencies where these signals can be seen, and I also have a sort of spiritual continuation of that, where I documented the signals being received also at 11.575 MHz, 11.950 MHz, and 12.450 MHz. So we went from seeing these signals at one frequency to seeing these at 4 frequencies. And that's kind of where I left it off. Now, since then, there has been, of course, some development. More people have been observing this. Some people in the professional sphere have also done it. And that is a research paper that I will probably be quoting quite a lot here in this video. So again, it will be linked in the description. I'm gonna pull it up right now, so I'm not just making things up, because I can't remember what happened like 5 minutes ago. Signal structure of the Starlink KU band downlink. And this is a paper published by a few people at the University of Texas at Austin, Department of Electrical and Computer Engineering. And it was published in August 2023, so a few years later, 2 years later. And again, it is linked in the description if you are interested in the technical side of the Starlink internet. They actually go in the details of the downlink structure, and they conclude that these narrowband signals are what they call leakage tones, and that they are some sort of byproduct of the transmitters, of the modulators on the satellite. So up until that point, I thought, and I'm pretty sure many other people also believed, that these are Doppler tracking beacons, that maybe they carry some low rate data, because if you were actually looking at them, they seem to sort of pulse around. Some of the peaks would turn off, some would turn on. It almost looked like that it is conveying some data, but according to this paper, it is some byproduct of the OFDM modulation of the downlink. So it might not be intentional emissions, and this is where I want to say in the video. If you are watching this in the future, what you will see in this video may not be replicable anymore. And the reason for me saying that is, well, if these are unintentional emissions, it's possible that the future generations of Starlink satellites will just get rid of them. But also, if you compare some of the screenshots or the initial screenshot in my blog post, where I was tuned to 11.325 megahertz in November 2021, and it's actually almost exactly 3 years ago, so now it's late November 2024, there is basically no activity, or there is very little activity today at that frequency compared to 2021. So despite there being several times more active Starlink satellites, the narrowband emissions, I'm still gonna call them beacons because I'm just used to it, but it's not intentional beacons, but the beacons are much more rare, it seems like, today than they were before. However, if you actually read the paper, it also suggests that these beacons appear at every single guard band between every channel, as well as directly in the middle of each channel. So here they conclude that the Starlink channel bandwidth is 240 megahertz. In the FCC listing for Starlink, it says that the channel bandwidth is 125 megahertz. Okay, in both cases, it comes out to a frequency of these beacons appearing being spaced 125 megahertz apart from each other. What I just said probably makes no sense because I'm not very good at conveying what I'm trying to say. So we are going to pull up the FCC document, SpaceX Non-Geostationary Satellite System, Attachment A, Technical Information to Supplement Schedule S. I have no idea what that means, but I don't care, because if we scroll down, we find a nice and neat chart, visual chart of the frequencies used by Starlink. As you can see, it is divided into Ka band beams, downlink and uplink, and then Ku band beams. We only care about the Ku band the Ku band beams, because they are aligned with the cheap hardware that you can get. The Ka band beams are used for communications between the satellite and the SpaceX ground station that actually relays the data into the World Wide Web, whereas the Ku band beams are used for communication between the satellite and the actual individual user terminals. So here you can see that the entire band from 10.7 to 12.7 gigahertz is allocated for SpaceX communication frequencies. And that's 2 gigahertz. If we divide 2 gigahertz by 125 megahertz, we come up with 16 frequencies that are either a guard band between the different downlink channels or the center frequency of the individual channels. And according to the paper, the Texas University paper, that is where these leakage tones, these beacons, appear. Now, I knew this paper existed, but because I'm extremely lazy and stupid, I didn't actually read much of it because I saw some math equations and I just gave up immediately. So instead, I just took the LNB, put it outside again to monitor the Starlink frequencies, and I started noticing these beacons, even though they are more rare today, they seem to now appear at many more frequencies than the 4 that have been identified in the past. So the 4 original frequencies that were identified back in 2021 were 11.325, 11.575, 11.950, and 12.450. Now, with just those 4, I didn't really see a pattern there, even though I probably already could have spotted it. But when I was repeating the experiment today, or I mean this year, this November, I began to notice more frequencies where activity appears, namely 10.950, 11.075, 11.450, 12.075, and 12.325. And at that point, I have started to actually see that there appears to be some pattern, that they are spaced apart by multiples of 125 megahertz. So what I did is I simply extrapolated the entire 2 gigahertz allocated frequency range from 10.7 to 12.7, divided by 125 megahertz. I came up with 17 different frequencies. That's of course because we are also including the 0th multiple basically. And I started monitoring the traffic there. Now, I didn't really have a good way to do it because obviously I have one SDR and I want to monitor 17 different frequencies. I don't have 17 SDRs. I only have like 16. So no, that's a joke. I don't have them. Okay, shut up. I don't have 17 SDRs, and if I did, that would be quite annoying to set up. So what I actually did is and by I mean ChatGPT, wrote some Python script that uses a HackRF to basically jump between all of these frequencies. So it starts at 10.7 gigahertz, records the spectrum there for roughly half a second, then generates an FFT plot, the spectrum plot, moves 125 megahertz up, repeats it, and goes all the way down to 12.7 gigahertz and then comes back to the beginning. By running this script and jumping between all of the 125 megahertz steps in the Starlink downlink band and generating spectrum plots from them and then displaying all of those plots on the screen at once, which I did simply by basically making an HTML page that displays all of the images and auto refreshes every 5 seconds. I let it run overnight and came up with this time lapse, and I'm gonna play it right now for me and in the video so I know what I'm talking about. In the time lapse you can actually see all 17 frequencies. So I was using the HackRF at 8 million samples per second, so each frequency is a 8 megahertz wide chunk and they are spaced 125 megahertz apart. And in the time lapse you actually can see every so often the activity appear on the spectrum, and those are actually the leakage tones or the beacons, if you want to call them, of the Starlink satellites. And if I'm looking correctly, I think they appear everywhere except 10.7, 11.7 and 12.7. In some cases we actually can see the start and end of the actual wideband internet traffic, although that is much weaker than the beacons, than the leakage tones, intermodulation tones, whatever they actually are. And yeah, that is exactly what the University of Austin paper described. The leakage tones appearing in the center of each channel and in the center of the guard band between each channel, which comes out to 125 megahertz spacing. So in practice, that means that there isn't one frequency where you can receive Starlink. There aren't 4 frequencies as we thought. There are at least like 10 of them, at least in the little experiment that I ran overnight. So the way I actually did this is I just took an extremely cheap LNB that I bought specifically for this video. It's a PLL Ku-band LNB, again 9.75 GHz local oscillator. I tied it with a piece of wire to the railing on the house balcony, aimed it roughly 45 degrees north, 45 degrees elevation, roughly northeast maybe, it doesn't really matter because the Starlink satellites are everywhere, and I just let it run overnight and it was able to receive all of those signals. I already knew that there were more frequencies like this. I didn't care particularly about finding all of those frequencies. What I really wanted to know, or what I really wanted to see, is which frequency has the most activity, which frequency you should tune to if you want to repeat this experiment to have the highest likelihood of there being a signal. And I believe the one that had the most activity, or at least tied with the other frequencies that had the most activity, was 11 for 50 megahertz, which is actually quite convenient because 11 for 50 minus 9750 is exactly 1700 megahertz, which is just about in the range of an RTL-SDR receiver or an RTL-SDR compatible receiver, and it is also well within the IF output range of a standard Ku-band LNB. Okay, so I kinda need to pause the video here. I've noticed in editing, now that I'm looking at the time-lapse again, that the frequency of 10950 megahertz seems to be even more active than 11450. Ultimately, it doesn't really matter with an RTL-SDR and the universal 9.75 GHz LNB. Anything between 10700 and 11450 will be receivable. And I'm also now realizing that maybe in different parts of the world, different frequencies may be at different activity levels, so it's something you may have to experiment with. I'm not really gonna edit out the rest of the video where I just say 11450 is the best. It's still applicable, the principle is the same, and if anything, the lower frequency bands maybe even easier to receive with SDRs, because after being down converted into the IF range, the SDRs will actually be more sensitive at those lower frequencies. Probably doesn't really make a difference with the massive conversion gain that TV LNBs have, but yeah, it just doesn't matter. What I'm trying to say, just look at the time lapse, you can see for yourself where the activity happens. This frequency also appears to have the strongest beacons. I don't care, I'm gonna be calling them beacons, just keep in mind that they are not real true beacons like on other satellites. And they also seem to occupy the biggest bandwidth. So again, referring to the Austin paper, probably for the last time, they noticed that in the guard bands in between the two 40 MHz white channels, so you have a 40 MHz white channel with a 10 MHz guard band, so in total that's 250. They noticed that in the guard bands there appear to be combs, is that how you pronounce it? Basically wider groupings of these leakage tones, whereas in the center of each band it looks like there's only one of them at a time, and that also appears together with the internet downlink traffic. And you can actually see it in the time lapse that I made in some of the pictures, and I'm gonna extract some still frames. And for example, the 11450 MHz band, or the 11450 MHz, there appear to be those wider groupings of beacons, whereas something like 11325, you only get one strong tone in the middle, and that is flanked on both sides by what looks like blocks of digital data. Well, what looks like, that's exactly what it is. That's the actual internet traffic. One last thing I want to say about the time lapse before we move on to a practical demonstration, which is what you've probably came to this video for. The last 1, 2, 3, 4, maybe the last 5 frequencies, beginning with 12.2 GHz, those, even though those are well within the range of the HEC-RF, when we talk about the down-converted intermediate frequency, you can see that the noise floor shape begins to distort. That's because the LNB at that point is not really, it's not rated to output those frequencies. Obviously it outputs them, it's not rated to output them well. In a conventional satellite TV receiver, it would command the LNB to actually switch to a higher frequency local oscillator. So the entire range of the LNB would basically shift roughly 1 GHz higher. You can't really do that with an SDR without some modifications, and I actually have that on my blog post. So, how would you actually go about receiving the Starlink beacons now? Well, in the exact same way that I described in my original blog post, except you just use a slightly different frequency. I haven't done it on video. There are actually videos on YouTube where people showcase receiving these. Some of them have suspiciously similar diagrams to what I drew in GIMP back in 2021, although this is such a simple thing that anyone would come up with it on their own, so I'm not gonna claim that I came up with something here. But I figured it's my turn to make this video, right? Alright, well, here's the setup. Originally I wanted to have like a time-lapse recording of my laptop outside, so you can actually see it receiving the signals with the very simple setup. In the end, you can't see anything on the screen because of the sun glare, so I'm just going to fake it by overlaying a recording I captured with my HEC-RF in my desktop computer. And I'm probably also going to speed up the footage, because what I didn't really mention in the original voiceover, as you can tell I'm doing this later again, is how long it can take between some signals appearing. So don't be discouraged if you tune to one of the active frequencies and you don't see any activity immediately. It can take probably up to like 5 to 10 minutes for something to appear. Again, based on what I've learned in that Austin University paper, it probably is going to depend on the amount of just active Starlink terminals in your vicinity, which maybe adds another interesting dimension to this, where you can use this LNB to estimate the amount of Starlink traffic in your area. But you will be able to see on the screen recording that every so often the beacons do appear, and I'm going to point that out on screen with some text overlay so you know what to look for. So let's go over the entire setup as you see it laid out on the table. Obviously, the first thing is the LNB. We kind of talked about it already. Here in Europe, standard LNBs use 9.75 GHz local oscillators by default. In other parts of the world, you may have different LNBs with different local oscillators available. You will just have to do the math yourself, just simply subtract the local oscillator from the RF frequency. But I think usually it will be around 9.75, maybe 10 GHz. Maybe some LNBs will use 10.5 or 10.7, and I have no idea what American LNBs use because, for whatever reason, American TV companies like DirecTV and Dish, they don't really specify the specs of the LNBs, and it's weirdly difficult to even look up the downlink frequency ranges that their satellites use. I don't know why. It's probably because, it's a monopoly. They don't really have to. But again, I think a Ku-band DirecTV LNB would be able to do it, especially considering that the Starlink downlink band covers the entire 2 GHz basically. After the LNB, we have a short piece of coax. Normally, you would probably be using a much longer piece. LNBs are designed to push the down-converted signal through a very long run of coax cable, so they have very high conversion gains. You might want to use an attenuator in front of your SDR if you can get one. If you can't, then just start your SDR with the lowest gain available. It's not really much about damaging the SDR, but more so that you will probably just overload it and your dynamic range will be quite low. It doesn't really matter. After the LNB, after coax, we have a little silver box that you can see on screen. This is called a bias T, or a power injector. You may be thinking your SDR already has a bias T that would power the LNB. However, SDR bias Ts, if they are equipped with one, they are going to be between 3.3 and 4.5 volts. LNBs like this require 12 volts. In reality, they require between 12 and 18 volts, and the voltage level is used for some polarization signaling. You don't need to worry about that because Starlink uses both left-hand and right-hand circular polarization, so no matter what your LNB is, it should be able to receive them. So all you have to do is supply the LNB with 12 volts, most likely, because that's going to be the easiest to obtain from common power supplies. Ideally, you would just power it with something like a lead-acid battery, because any cheaper, lower quality, poorly filtered switch mode power supplies can introduce noise into the system. Again, and I'm saying this a lot, it probably doesn't really matter. Just try with whatever 12 volt source you have, as long as it's not like outputting high levels of AC voltage leakage or whatever. So the power injector that I have, it was bought again off the shelf standard component. This one was specifically bought for powering LNBs, so it is rated for the frequency ranges between like 800 MHz and 2.4 GHz. You can get cheaper ones, more generic ones that are meant to power terrestrial TV antennas. Those will usually be rated only up to 800 MHz, but it doesn't really matter. The LNB again has massive conversion gain, it's just going to push the signal right through. The impedance at those higher frequencies may not be ideal, but again, the LNBs, they are designed to, just take it, just deal with it. So the bias T, it has 3 connectors. It has the combined RF and DC connector, where you connect your LNB. It has a DC connector, where you connect your power supply, and then it has an RF only connector, where, as the name would imply, only the RF will pass through, so that's where you connect your SDR. You have to be very careful. First of all, if you're going to be buying one of these power injectors, make sure it's not an amplifier, because some look the same as a power injector but have an integrated amplifier for terrestrial TV. Also make sure that if you are buying one with a switch mode power supply, that it is a 12 volt supply and not a 5 volt one, but you can also just cut off the leads and supply your own power. Make sure the polarity is correct, check with a multimeter if you have one, and most importantly, make sure to not connect the power injector backwards. This is something that's happened to me, that's happened to many people with SDRs and satellite reception, because if you do that, then you are feeding the DC voltage into the SDR instead of the LNB. Then, after bias T, we have the SDR itself. Between the bias T, or between the power injector and the SDR, is where you would put your attenuator if you had one. Don't put it between the LNB and the power injector, because some attenuators may not be rated to pass through direct current, so you would put it right at the SDR. Here I am using an RTL-SDR V3 with no attenuator, and the LNB blasting it directly with like 10 centimeters of coax, and it's doing just fine, so make of that what you will. And that's basically the entire setup. The LNB, despite its use without a dish antenna, so normally the LNB would sit in the focal point of a dish antenna, where it would receive the signals collected by the dish. Here we are using the LNB as the antenna itself. Now, despite the LNB beam width being quite wide to cover the surface of the dish antenna, it is still a largely directional antenna when compared to something like a dipole. So you can take the LNB and sort of move it around if you want to increase your chances of spotting some downlink signal. But again, if you just leave it sitting pointed straight up, it will eventually come across a Starlink satellite, or rather, eventually a Starlink satellite will fly through the beam of the LNB. It's also probably going to be more likely to pick up signals when aimed directly up. We are looking at signals intended for Starlink terminals nearby, so it probably would mean that most of the traffic is going to be from high elevation satellites. If you are at high latitudes, like Canada, it may be better to aim the LNB south due to the inclination of the Starlink satellites, and there being much fewer satellites in the high inclination polar orbits than there are in the lower inclination main orbital groups. Again, just like with the frequencies active at your location, it may take some time and some experimentation to see which angle the most activity is going to be coming from, which parts of the sky are going to be most RF active. Different satellites will also have different activities observable. Again, this is something that the paper mentions, that it appears to be random which satellite actually has these leakage tones, these leakage beacons, and the patterns that each satellite emits. So again, even though there may be plenty of satellites in the beam of your LNB, you may not be getting any narrowband activity. I'm trying to think about what else to say because the original take was kind of bad. Arguably the most fun, engaging thing that you can do with these beacons once you are able to receive them is switching your SDR software to USB demodulation, single sideband demodulation, and then positioning your tuner, your VFO, to a frequency where these beacons often transit, because of course the Doppler shift at 11 GHz is so prominent that you will see the beacons basically will appear to be shifting constantly in frequency from high to low. So if you take your audio demodulator or your audio tuner and put it somewhere in that range that the beacon seems to traverse, you will actually be able to hear the Starlink satellite, the Doppler shift of the Starlink satellite as it is passing by. And I'm going to play some examples full screen right now. Of course, because the beacons, if you tune to one of the frequencies where there are the entire clusters of beacons and not just the singular tones, you will be able to hear each satellite multiple times as it passes, as the different tones pass through your tuned bandwidth. Or you can just keep retuning your SDR to constantly have the signal transiting through your audio bandwidth and hear the actual sound of the satellite. There isn't really much else you can do with these, so I think that's about it. And I am now going to cut back to the original voiceover. I think it's a nice experiment to actually interact with Starlink in some manner, although some of you may just have the Starlink terminal, so you are interacting with it in the way it's supposed to be interacted with. But for a simple experiment, seeing some traffic with your SDR from Starlink satellite, this is perfectly acceptable. Now, there may be other things to do with an SDR on Starlink that I'm going to leave off for another video. As you know, we have looked into the band plan of the Starlink downlink. It also uses the Ka band, or the 20 GHz band, as it probably should be called better, for downlink, and then 30 GHz for uplink. We only care about downlink. I did this exact same experiment, let's call it, with a 20 GHz LNB that I have, but I was not actually able to detect any narrowband emissions from these Starlink satellites. Maybe that's just because there is no Starlink ground station nearby, and the Starlink satellites are basically big patch array antennas, and they use beamforming. So even though the satellite is in your line of sight, you can aim your antenna at it. If the satellite is not actively directing the beam at you, or at least in your general area, you will not be able to see the downlink. So even though the satellites in my line of sight may be active in the 20 gigahertz downlink band, it doesn't mean I'm gonna be able to receive them if the ground station is far away from me and the satellites are directing their downlink beams away from my location. So I may have to revisit that in a future video, except we're gonna be using a dish antenna to just brute force as much gain as possible. So even if the satellite is not aiming directly at me, even if I am in like a weaker sideband, I'm still gonna be able to receive it. Another thing that I maybe want to do, and that I maybe will do in a video, is trying to receive some of the telemetry channels. So if you look again at the band plan, the FCC spectrum allocation, there are little purple blocks, and if we go to the description or to the key, those are SpaceX TT&C frequencies, which stands for telemetry, tracking, and control frequencies. So all of the other traffic that we have been looking at up until now is the actual broadband, the actual internet traffic that's actually supporting the Starlink internet service, whereas TT&C, the telemetry and tracking frequencies, are for the satellites themselves, and this is what the satellite would be transmitting in its early stage. So right after launch, I really want to try intercepting some signals from satellites that have been just freshly launched, because those are not in active internet service yet, and then they may be transmitting some data there for tracking and some telemetry there. It's probably going to be encrypted, but still it's going to be fun trying to receive that. In the same FCC documentation, it also says that the TT&C antennas are omnidirectional, so the beamforming aspect should not be a problem for me. But although that also means that the signal is going to be much weaker, so definitely we will have to use a dish antenna. And it also says that the TT&C downlinks are much narrower. Now, if we actually go to the band plan, it says the TT&C channels have 50 megahertz allocated, which is still a lot, but it's nowhere near as much as the 250 or maybe 125 megahertz, depending on how you want to look at it, channels for the service downlinks. Still, 50 megahertz is much more than an RTL-SDR or a HKRF can handle, but, maybe there have been some developments, and maybe I now do have an SDR that can sample all of 50 megahertz, or maybe all of 100 megahertz, or maybe all of, 150 megahertz. We're gonna see in the future. It's a bit of foreshadowing for you. And with that, I'm going to conclude this video, because we are at, let's see, 1 hour and 5 minutes of raw audio recording, so it's going to be fun trying to edit that down. For now, that's going to be all from me, and I'll see you, in like another 5 months. Bye.